In this chapter, we'll be looking at electrochemistry, which is the study of the relationships between electricity and chemical reactions. We'll be looking very closely at how electrons get transferred from one species to another in these types of reactions. And so it's important that we begin by a review of determining oxidation states. So what is oxidation? Remember our old saying, Leo says Ger. Leo, loss of electrons is oxidation, and gain of electrons is reduction. And so we use oxidation numbers to keep track of which species is gaining electrons and undergoing reduction, and which species is losing electrons and undergoing oxidation. In this example, zinc, which is uncombined with anything else, has an oxidation number of 0. On the other side of the equation, as a product, it has an oxidation number of +2. Since it's gotten more positive by a factor of 2, then it has lost 2 electrons and undergone oxidation. Our hydrogen here has an oxidation number of 1, and there are 2 of them. Over on the product side, we have H2, a hydrogen molecule, which will have an oxidation number of 0. And so if we go from an oxidation number of +1 to 0, we've become more negative. Gain of electrons then is reduction. So let's do a quick review of how to assign oxidation numbers. Rule number 1 states that elements that are in their elemental form have an oxidation number of 0. So what this means is if you saw just plain old aluminum metal, it would have an oxidation number of 0. That's aluminum in its elemental form, just plain old solid aluminum. Or if we had oxygen gas, O2 or H2, uncombined elements are going to have oxidation numbers of 0. Rule number 2 says the oxidation number of a monoatomic ion is the same as its charge. So in other words, if we have a sodium ion with a charge of a +1, then its oxidation number would be +1 as well. Rule number 3, nonmetals. Since nonmetals tend to form negative ions or anions, then they're going to tend to have negative oxidation numbers, although they can have a positive oxidation number depending on how they're bonded to other elements. Also important is that oxygen, similar to the charge of an oxide ion, is going to be an oxidation of a -2. That is, unless it is in a peroxide, in which case it is a -1. The peroxide ion has a formula of O2 -2. Hydrogen forms an ion with a +1 charge, and typically a hydrogen is going to have a +1 oxidation number as well, unless it is in a metal hydride. When it's bonded to a metal, in that case the hydrogen will have an oxidation number of a -1. The sum of the oxidations in a neutral compound, for example ammonia, is 0. So hydrogen, when bonded to a nonmetal, is going to have a +1 oxidation number. There are 3 of them, so that gives the hydrogen part of this a +3. And that means that the nitrogen, since there's only 1 of them, is going to have a -3 oxidation number in order for the sum to equal 0. The sum of the oxidation numbers in a polyatomic ion, for example, the sulfate ion, would have to add up to the charge on the ion. So in this case, our oxidation numbers are going to add up to a total of -2. The oxygen in this compound is going to have an oxidation number of a -2. And since there are 4 of them, that's going to be a -8. And for the sum of these to add up to a -2, that means our 1 sulfur has an oxidation number of a +6. Redox reactions, the equations of redox reactions, can be pretty cumbersome to try to balance, and so we use a method called the half reaction method to accomplish this. And so these redox reactions are depending upon electrons being lost by one species and gained by another species, which is all happening at the same time. When we're trying to balance these equations, we treat the oxidation and the reduction as two separate processes. So we'll show which species is losing electrons and how many, and which species is gaining electrons and how many. And then when we've done that, we'll add them both together to get the balanced equation for the overall reaction. If we were to titrate in an acidic solution sodium oxalate with potassium permanganate, the permanganate ion gets reduced, and it is a dark purple color here, gets reduced in appearance. It is a lighter pink color by the oxalate ions. Once all of those oxalate ions have been consumed, if you continue to add the permanganate to that, the solution in the flask once again becomes that dark purple color, since now we have an excess of that permanganate ion. Our first step is going to be to use the rules for assigning oxidation numbers and determine which species is gaining electrons and undergoing reduction, and what species is losing electrons and undergoing oxidation. From that point, we'll pull out the oxidation and the reduction half reactions. If we look at the reaction between the permanganate ion and the oxalate ion, we'll start by assigning oxidation numbers to all of the species involved. So our oxygen in the permanganate will be a -2, and the manganese would be a +7. Looking at our oxalate ion, the oxygen is a -2, and the carbon is a +3. And then when we look at the product side, we see we have the manganese ion with a 2+ charge, and so its oxidation number then would be a +2. And on our carbon dioxide, for our oxygen, again, we're going to have an oxidation number of -2, and our carbon will be a +4. So what changed in terms of its oxidation state? Well, we had the manganese on this side of the equation with a +7 oxidation number, and on this side of the equation with a +2. So it's gotten more negative, meaning that it has gained electrons and undergone reduction. The oxygen here is -2, and it's a -2 on the product side as well, so it's not undergoing any changes in terms of the redox process. But in our oxalate ion, we have carbon starting out on the reactant side with a +3 oxidation number, and on the product side with a +4. And so, since carbon has gotten more positive in terms of its oxidation number, then it has lost electrons and undergone oxidation. So the next step is going to be, now that we've determined what's undergone reduction and what's undergone oxidation, is to pull out those half reactions. Now, since our manganese went from a +7 to a +2, it got more negative, which means it gained electrons, since electrons have a negative charge. And since it went from a +7 to a +2, then it must have gained 5 electrons. I'm pulling out our other half reaction. So first of all, I have my oxalate ion here with 2 carbons, and the carbon is forming carbon dioxide on the product side. And so my first step is going to be to even out the atoms, so 2 carbons on this side and 2 carbons on this side. And then when I take a look at my oxidation numbers, the carbon on the reactant side was a +3 oxidation number going to a +4 oxidation number on the product side. So then each of those carbons then, since this has gotten more positive, have lost 1 electron. Since there are 2 carbons here, then our total electrons lost will be 2. So we can't have a reaction where one species is gaining 5 electrons and the other one's losing 2. How can this gain 5 electrons if this only lost 2? Our electrons lost and gained have to be equal. And so in order to do that mathematically, we would multiply both by the least common multiple. And so I would multiply this half reaction then by 2, which would give us 10 electrons gained, and I would multiply this reaction by 5, which would give us 10 electrons lost. And our two half reactions then end up looking like this. And so we can add those two together and we'll end up with an equation where our electrons gained are equal to our electrons lost, and that puts everything else in the proper stoichiometric proportions for that to happen. Next, we'll balance out the oxygens by adding water. I'm seeing 28 oxygens on the reactant side, and I'm seeing 20 oxygens on the product side. So that tells me that I'm going to have to add 8 waters to balance out those oxygens. Next, we'll have to balance out the hydrogens by adding hydrogen ions. We just added 16 hydrogens to the product side, so that means we're going to add 16 hydrogen ions to the reactant side. We can cancel out our electrons gained and lost, being an equal number, and we're left with our balanced reaction equation. So we did balance the entire problem on the previous slide, and here are a few more of the rules. Now, if you're writing the rules down, you'll notice that I did these in a slightly different order than the order that they're given in your textbook. Either way will work for you. Now, if we were going to balance a redox equation in a basic solution, we would follow the exact same steps as we did for the acidic solution. The only difference is that we would add hydroxide ions on each side that will balance out or neutralize the hydrogen ions that are there and create water in its place. And so even though there are a lot of steps involved in balancing these types of equations, you'll find that as you get a little bit more practice with them when we do them in class, they're actually pretty easy. So that's all for now.